In this video, we're going to look at symmetries of graphs and determine if a function can be classified as an even function or an odd function. We'll begin by looking at the first type of symmetry, a reflection symmetric type graph. That's a figure that can be mapped onto itself by a reflection over some line L. That line L can be referred to as a line of symmetry or an axis of symmetry. So if we take a look at this particular parabola, we would identify that the axis of symmetry is at x equals -2. That is because if we take the shape of the parabola and reflect it around that particular line, it would produce its own graph. If we look at this particular figure, the axis of symmetry would be at x equals 1. As you can see, we spin it around this particular line or axis, and we produce the same figure. A graph could also be 180 degrees rotation symmetric. We could also refer to that as point symmetry. That's where a figure can be mapped onto itself under a rotation of 180 degrees around point P. That point P would be referred to as the center of symmetry. In this diagram, that point P would be at -1, 2, because it is here where we would rotate it and the graph would be mapped onto itself. In the diagram above, that center of symmetry would be at 2, -3. Although symmetry can occur anywhere, I'm interested in 3 specific locations. Under reflection symmetric, I'm interested in when we have symmetry with respect to the y-axis as well as the x-axis. I'm also interested in 180 degree rotation symmetry when that symmetry is with respect to the origin. When a graph is symmetric with respect to the y-axis, you will be able to show that every point xy as well as its reflection image -xy is on the graph. So if we do have a diagram, let's say the one on the left, that happens to have a point 3, 1. Since x is 3, -x would be -3, and notice that both share the same y-coordinate. But just because one pair of points happen to meet this criteria, that's not sufficient to meet this definition of symmetry with respect to the y-axis. You have to show that all the points will be symmetric. Again, on the graph on the right, if we happen to have a point 2, -3, and x is 2, then -2, -3 would also have to be a point. And not only those points, but all the points that are on the graph. Another possibility is having symmetry with respect to the x-axis. In this case, every point xy, as well as its reflection image x, -y, would be on the graph. The issue is that the relation will most likely not be a function, because, like our diagram below, if you did have the point 4, 3, where x is 4, you're also going to have another 4 coordinate, 4, -3, where the y's are opposite, and in this case it would fail the vertical line test. When it comes to point symmetry, we're interested in symmetry with respect to the origin. That's where every point xy, as well as its reflection image -x, -y, is on the graph. If we look at our first example, we see that our point of symmetry is going to be at 0, 0. If we had a point 2, 3, since x is 2, we'll need a point that's -2. Just as y was 3, we'll need to say -3 for the other point. And then we should be able to spin it 180 degrees around the origin. In our second example, we happen to have a point of symmetry that's not actually on the graph. That's why the color is slightly different. But we can still have a point on the graph that's 1, -2. If x is 1, then -x is -1. And if y is -2, then the negative of a -2 would be +2. So although you may have a point of symmetry that's not actually on the graph, you can still show that 2 points are going to meet that reflection image as well as all the other points. Some functions can be classified as even functions or odd functions. We'll begin with an even function, which is a function that meets the following definition. F of -x will equal f of x. So let's take a look at an even function, f of x equaling x squared. If we had a point 2, 4, then we can say f of 2 equals 4. But the definition says that we also need to show f of -2, which happens to be the same height of 4. Not only are those points, but all points will be symmetric with respect to the y-axis, meaning the corresponding points x and y and -xy will both be on the graph. We will be able to reflect it around the y-axis. Odd functions meet a slightly different definition. It still begins with f of -x, but this time it equals the opposite of f of x. An odd function would be f of x equaling x cubed. If we were to take a point 1, 1, f of 1 would equal 1. What I would need to show now is that f of negative 1 equals the opposite of 1, which in this case it does, it equals negative 1. Odd functions share one particular property. They are symmetric to the origin, meaning the corresponding points x and y and negative x, negative y will both be on the graph, and you will have 180-degree rotation symmetry around the origin. To show that a function is even or odd, it is not sufficient just to select an x and its negative x and show that those heights are the same for an even function or opposite to each other for an odd function, because those 2 points may only be the points that work for the definition and the rest of the corresponding points don't. We need to show that every value of x and negative x meet the definition, which will require us to do a proof. In our case, we're going to prove that f of x equals x squared minus 4 is an even function. And to do that, we will do a composition, where we plug negative x into the x spot of our equation. So f of negative x equals parentheses negative x quantity squared minus 4. I expect to see the negative x in quantity being raised to second. Do not simplify. That will be the role of the second step, where we take negative x times negative x and realize that's the same as positive x squared minus 4. What I'm looking for is the fact that x squared minus 4 is defined to be f of x for this particular example, and I can replace that and come up with our original definition of an even function, f of negative x equals f of x. So for my proofs, I would expect these 3 steps. And when we're done, we can show that f of x is an even function because it will be symmetric with respect to the y-axis. Proving an odd function is not that different than proving an even function. So in order to prove that g of x equaling 2x cubed minus 4x is an odd function, we will again use a composition in which we plug negative x into our equation. This will require us to plug negative x into 3 different spots. G of negative x equals 2 times the quantity negative x, all raised to the 3rd power, minus 4 times negative x. Let me emphasize, for my proofs, I do not want you to simplify in the step, I just want you to show that negative x was plugged in. It is the next step where you will simplify, and a negative x times the negative x times the negative x times 2 works out to be negative 2x cubed, just as negative 4 times negative x works out to be positive 4x. The only difference between an even and odd function is we're expecting our odd function to be the opposite of what we began with. So you should be able to factor out a negative from the expression, in this case negative times the quantity 2x cubed minus 4x. Realize that in the parentheses, 2x cubed minus 4x is our original function g of x, and we can come up with the definition where g of negative x equals negative g of x. The only difference between an even and odd function is that an odd function you should be able to pull out a negative 1 because it will be the opposite of your original. And in the end, g of x is an odd function, which means it is 180-degree rotation symmetric around the origin. Taking into account the various types of symmetries and the properties of even and odd functions, we should be able to look at a graph and determine if the graph is going to be even, odd, or neither. For the 6 examples I'm about to do, in the case of neither, I will show you why it's neither. Otherwise, I will just show you the correct answer. For instance, the first problem is neither. Let me show you why it's not even. If I was to reflect it around the y-axis, the graphs would not match up. If I thought it was odd, I would not be able to rotate it 180 degrees around the origin and match up. Therefore, this graph is neither. The graph on the right, on the other hand, is symmetric with respect to the origin. Therefore, I should be able to rotate it at the origin and produce the same graph. Our next example on the left is an even function because it can be reflected around the y-axis. Meanwhile, our graph on the right is neither even nor odd because it cannot be reflected around the y-axis, nor can it be reflected around the origin. And as we've come to our last slide, I have 2 more examples. The graph on the left would represent an even function, as it is reflective with respect to the y-axis. But before I give you the answer to the graph on the right, please note the following: that this graph is actually reflection symmetric if you understand that it is cyclical in nature, meaning it's going to repeat. We can actually show that there will be a line of symmetry at x equals -5. We could show there's a line of symmetry at x equals -3, as well as x equals -1, x equals 1, x equals 3, x equals 5, and so on, again, because of the cyclical nature of the graph. We can also show that this graph is 180-degree rotation symmetry at -4, 0, -2, 0, 0, 0, 2, 0, 4, 0, and so on. So if we're going to show it's an even function, it needs to be symmetric with respect to the y-axis, which in this particular case, it is not. If you're going to show it's an odd function, you need to show it's symmetric with respect to the origin, which in this particular case, it is. And that's why this one is classified as an odd function.